think I'm ready now. I have some demonstrations, and I have quite a few. I bet by the end of the week, you'll probably see over 20 demonstrations today. This week, I mean. The demonstrations, some of them I will ask you about on the test, but most of them are just kind of to bring home the point of what's going on here. Let's take a look at, if you're on page 383. 383. Okay, here we go. We're getting there. All right, so there's going to be a set of numbers. I do want to get that done. Does everybody have their packet with them? Do you have your packet? If you get your packet, I'll be doing that today too. Let's take a look. Okay. First of all, we talked about if we talk about gases, the most common gas we're going to talk about is air. Air is actually a mixture of gases, and about 80% nitrogen, maybe 20% oxygen. You got a little bit of stuff mixed in there too, but anyway, that's pretty much what air is. We go to other planets, we don't find that mixture. If you ever watch Star Trek or anything, they talk about M-class planets. The temperature just about right, and the oxygen, it's enough oxygen in there you can breathe, and they like to call those M-class planets. You don't have to have your book, but if you want to like to write little notes in your book. Okay, sure, you can do it. All right. So anyway, some numbers you're going to see here, and I did convert these into miles, make it a little bit easier for you. Mount Everest is about close to 6 miles up there. It's about a little more than 5 miles, and certainly we're not going to have anything above that as far as clouds or anything. I guess if you talk about weather, that's pretty much it. Even your planes are going to be maybe around here, maybe down here. Anyway, so a number they're going to use all the time is 30 kilometers, because they say about 99% of the atmosphere is found below 30 kilometers. So you'll see that number all the time. All right. The next thing we talked about was let's talk about how air is different. And one of the pictures I had you look at will look like this. And we had to think differently. We had to think differently because, again, a column of solid, a column of steel, I wouldn't see this. I'd see the evenly distributed particles. A column of water, same thing. But when you have a column of air and you have the weight of air on top of it, it's going to be a little more spongy, isn't it? Matter of fact, this air here is going to press down here. And so we actually live at the bottom of an ocean of air, and we live in the most dense air that we can get. I had somebody many years ago do a project. They were wondering, what if you go under mine? What if you're a miner and you go underground? We have some mines that are actually, half a mile down. And that's scary. That'd be kind of scary to go down, that far and think, wait, how much earth is above me? And the question she asked was, does the pressure keep increasing as you go down? And they had real numbers, and she looked it up. It was from the mining corporation, and it does. It actually, the pressure keeps going higher and higher as you go down, even underground. So even though I say we live in the highest pressure, I don't live in a mine half a mile down, but most people live here. All right, so then we also found out that we have some density numbers, and even though I like to use this one because this is the closest to room temperature, it looks like the density of water is more dense than water. Density of air is more dense than water, but it's not because of these units here. This number is actually 0.00121 in grams per cubic centimeter. So you should be able to do that. I'm actually going to put one on test. They'll say use show factor label and convert this into that. Okay, that should be easy for you. Then we looked at some other numbers. For example, how many times greater? Let me see if I can find some numbers here. How many times greater is, this is how you do the factor label thing. How many times greater is the density of air than the density of helium? And it was about almost 7 times. And we're going to talk about helium also. What about the density of air versus the density of water? And we said that was almost 900 times, wasn't it? And so air is about 900 times less dense than water. All right, so I am being buoyed up. I actually am being buoyed up. If we use Archimedes' principle again, I'm actually displacing air, and the amount of buoyant force is equal to the what? What do you think? On a Monday morning, Ryan, since you came in late, why don't you tell everybody? I'm being buoyed up by A buoyant force equal to the what? Of? I'm not in water though. Right now, right? Like right now, am I being buoyed up? Yes or no? Okay, am I displacing air? Is air a fluid? Okay. Does Archimedes' principle have to do with fluids? Okay. So am I being buoyed up? Okay. So it's equal to the weight of what? Go ahead, Ryan. How much? Right. And the air doesn't weigh that much, does it? So even though I have a buoyant force on me right now, that doesn't mean I'm going to go up. See, because I know my weight is greater than the buoyant force. Now, another thing I'd like you to know, and I think I put this in here, one of the pages in your packet, I said there's a series of numbers that you need to kind of make sure you can do. Let's see if I can find here. Here it is. So find this, oops. Yeah, here it is. Find this page here. And even though you had the lesson on Thursday, see if you can come up with this. What is the mass of air with a cross-sectional area of 1 square centimeter all the way to the top of the atmosphere? If you remember, that was at 30 kilometers up. All right, what is the mass? Do you remember it? How much?
1 kilogram.
You're right. It's okay. So, and that's what this picture is right here. And then the question was, what is the weight of the air in that straw that goes all the way 18 miles up in the air? What is the weight of that air? Yes. Excellent. Even on Monday morning, this is great. Thanks. What is the number of square centimeters in a square meter? And we talked about that yesterday or Thursday. A square meter would be 100 centimeters that way and 100 centimeters that way, like that. So how many square centimeters would be in a square meter? You know, you remember that?
2 billion.
How much?
2 billion.
No, that's three-dimensional. If we do three-dimensional, you'd be correct.
Oh, it's square meter. Oh, 10,000.
All right, so 10 to the second times 10 to the second is 10 to the fourth. 10 to the fourth is 10,000. And so what they want to know is how many of those straws could fit in a square meter. And what's that number again? 10,000 or 10 to the fourth, right? So what would the mass of air that would be sitting on a square meter be? What's the mass of air sitting on a square meter? All right, somebody else. You did a good job. Somebody else. Ellie, you with me today? What do you think? What would the mass of air be sitting on top of a square meter? I'll give you a hint. A straw, a 1 square centimeter going all the way to the top would be 1 kilogram, and there are 10,000 of those in a square meter. So what's the mass of the air sitting on 1 square meter of a table? What do you think? Try it again. Let's go. If I had a straw like this and had a 1 square centimeter of area and went all the way to the top of the sky, that would be 1 kilogram. I want to know not per square centimeter, but per square meter, and there are 10,000 of these. 10,000 of those would fit there. Each of those would be 1 kilogram. So how many kilograms, what would be the mass of air sitting on top of 1 square meter of a table? 10,000. That's kilograms, right? What's the weight of air sitting on that? Yes?
Maybe 10 to the 3rd.
Okay, or 100,000, right? 100,000 newtons. And they said that a Pascal of pressure is 1 Newton per square meter. And so what would be the number of pascals on a square meter of table at sea level? And it would be 100,000 newtons per square meter, right? So what's the pressure of air? The pressure would be 100,000 pascals. And of course, humans don't necessarily like that, so they change it to kilopascals. So how many kilopascals are there? 100. Are you okay with the math on that? You might want to go back and do that again. This page right here is the one you want to read several times. And that's how they get all those numbers. If you just did it by yourself, if you read this one page and you did all the numbers yourself, I think you would understand that. So what I'd like to do is I'd like to show you, oh, by the way, another number that you should know is, what if I had a cubic meter? What if I was at sea level and I had a cubic meter way down here where the dense air is, where the real dense air is? If I had a cubic meter of air, how much mass would that be? You might remember that. That was from actually a problem. What do you think? What is the mass of a cubic meter of air? What do you think? Okay, it's a little bit greater than a kilogram, right? So it's pretty close to a kilogram, a little bit more than a kilogram. Got that? So those are some numbers we can kind of remember like that. So here's a problem with dealing with this word called air pressure, all right? And I'm gonna come back to that in just a minute. Here's the problem with air pressure. Find the right page here. In chemistry, there was a problem with this word called concentration. And how many ways could you represent the concentration of a solution? And one of them was grams of solute per 100 grams of water. That's somebody uses that. Molarity is moles of solute per liter of solution. Molality is another one. Percent by mass is another one. And unfortunately, there are several ways to represent the concentration of a solution. That's not this chapter, by the way. But the reason I'm telling you that is, how many ways can you represent air pressure? And the bad news for you is there's more than one. So let's take a look. If you in pascals, how many pascals would be what you might call normal atmospheric pressure? And we just calculated that. In kilopascals. How many kilopascals? So it's about a little over 100. It's about 100 kilopascals would be called normal atmospheric pressure. I'm going to talk about this today, and you know what humans do, though. Humans are pretty smart in a way. Do you remember we were talking about atoms in chemistry, and we said what's the mass of a proton? It was like 1.67 times 10 to the minus 24 grams or something like that. And you say, well, humans don't like saying that all the time, do they? So what did they say the mass of a proton was? I hereby declare that many grams is equal to what? One atomic mass unit. And even the world of charge, it was, I forget that number. I'll make it up. Times 10 to the minus 19th coulombs. And that's how much charge a proton had. And he said, why don't we just call that 1? And you were plus, and the electron had the same number of coulombs, you're minus 1. I like that. If you're an astronomer, the distance from the Earth to the Sun is 93 million miles, or even more than that, kilometers. But what did the humans do? If you're an astronomer, you'd say, what do they call it? What's the distance between the Earth and the Sun? It's called 1 AU, 1 astronomical unit. So if I'm reading a book and it says some planet is 13.5 AU, hey, you're 13.5 times further away from the Sun than the Earth is. And they do it all the time. Scientists do it, humans do it. Here's one of my favorite ones. You said you took scuba diving. I'll bet you probably talked about air pressure in atmospheres, because that's pretty easy. Guess what it is? If you're at sea level, what is normal air pressure at sea level? 1. I hereby declare the weight of that much air on top of you is 1 atmosphere. But if you go down about 33 feet down to the water, that weighs the same amount as all that air. All the air sitting on top of you above the water, and then you go under the water 33 feet, that much water weighs the same as 18 miles of air. And so then you go 2 atmospheres. And so what happens if you were to, for example, one of the number one rule about scuba diving is, if you were to be under the water and you were to take a big amount of air, what do you not ever do when you're coming up? How do you remember that, right? They made that point. Because you filled your lungs with air down here at 100 feet down. And you said, I ran out of air. I'm going to hold my breath. Well, you're in trouble. You're already in trouble. Because you filled your lungs with air under that much pressure. And now you're coming up, coming up, and coming up. What's going to happen to those balloons called lungs? They're going to expand, 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 and they actually will burst, and you can start bleeding, you could die. So even at a small scale, you would not want to go down and hold your breath and pick something up like that. Even that small amount of distance could make a difference. You want to be careful about that. All right, so I like this. I do like the word atmosphere. And here's 100 kilopascals. I can remember that. And then we have this thing called a barometer. So what I'm going to do is, chances are you have not read this. Is that correct? I'd like you to read that tonight, and we're going to talk a little bit about the history. For example, one of my favorite parts of reading here says, atmospheric pressure was first measured during the 17th century. Galileo noticed that the water pumps he designed were capable of pumping water to a height of about 32 feet. But he never adequately explained why. His disciple, Evangelista Torricelli, invented the barometer as he attempted to answer this question. Galileo, you're going to find out later in the second semester, he was incredible, what he could think of that no one else could think of, okay? And yet this was a little bit of a puzzle for him. You'll find out later, Isaac Newton, incredible thinker mathematically. But when he started to do the mathematics of the orbit of the moon, it gave him a headache every time. It didn't quite fit. He knew it had to fit mathematically, but it gave him a big headache. So there are some puzzles that people, even your geniuses, there are some things that, remember Einstein. Einstein had a great amount of trouble with quantum mechanics. He understood it. He actually started the idea. He helped start the idea. But there were certain parts of quantum mechanics that he had trouble accepting. It just seemed like the universe wouldn't be like that. Well, anyway, we're going to talk about this thing here called a barometer. And Torricelli made a barometer. And I am going to mention this several times. If you understand a barometer, you'll understand what's happening right now today in our weather. And I'll even give a little brief weather lesson tomorrow, a little 15-minute weather lesson, show you how to look at a map a little bit. I want you to imagine a bowl of mercury, okay? Everybody have a bowl of mercury? Now, we could make a barometer out of air, but it would have to be 30 kilometers tall. No, I don't think so. We could make a barometer out of water, but it would have to be about 33 feet tall. No. What if he had a liquid, a fluid, that was very dense? It was so dense that I could put the whole barometer right here. I'll take it. Now, today, a lot of your mercury barometers have been replaced with electronic things, haven't they? Any of you have a barometer on your app on your phone? Altimeter? Barometer? Oh, okay. All right. They actually have those. You can actually tell, hey, I'm half a mile above sea level, So you can do that. All right, so here we go. Let me explain to you what a barometer does, and this will make a whole lot of sense to you, I believe. Now, imagine a bowl of mercury open to the air, and then I have another tube of mercury. Let's say I have a long tube here. Let's say it's a meter long. I fill it with mercury, and by the way, that's not easy. It's really, really dense. You'd have to really hold it. You'd have to pour a little bit at a time like that. And then eventually, I might have to have somebody help me, but I would put my thumb over that tube, and I would turn it upside down, and I would stick it in the bowl of mercury. So for Monday morning, is everybody with me on this? Stick my thumb, I turn the big column of mercury upside down, and you say, don't do it, don't take your thumb away. And I do. I take my thumb away, and you see the mercury start to fall. You say, I told you so, you shouldn't have done that. And then what happens? It stops falling. What? No, this big tube of mercury and a bowl of mercury, and I saw it start falling, and it started filling up the bowl, and then it stopped. Why would it stop? Come on. Why don't you just pour all over the floor, All right, so, what do you think,
Because as the mercury comes out of the tube, it leaves a vacuum because there's no way for air to get.
Are you going to say the word suck?
No,
Okay, good.
because now there's empty space inside of the tube, so
Uh-huh.
air cannot get in.
That's right.
So the air from the outside pushes on the mercury and tries to get in, and then it keeps it.
Well, I agree that the air is trying to fill in that vacuum, and it's going to push everywhere, and it will actually push on the surface of this mercury here. So let me ask you a question. Which is greater? The weight of 76 centimeters, that's about 3/4 of a meter, everybody get the? The weight of 76 centimeters of mercury, or the weight of 30 kilometers of air? Which one's greater? Oh, I mean, I shouldn't say that. I shouldn't say weight per square centimeter. Let's say this is a square centimeter. That'd be a really tiny barometer. But per square centimeter, which one has more pressure? Which is force per area. This has a certain amount of weight, and that's your area. And this has the air has a certain amount of area. And if I compare every square centimeter, which one's greater? Which one's a greater amount of force? The weight of the air on that column, or the weight of the mercury? 30 kilometers of air, or 76 centimeters of mercury? Which one weighs more? Which one? They have to be equal. So what you want to do is you want to think to yourself like this. If I wanted to make a barometer out of air, I would need 30 kilometers of air, because that would weigh 30 kilometers of air in this column would equal the weight of 30 kilometers of air pushing on the bowl of air. So I could make a barometer 30 kilometers tall, but nobody's going to do that. There have been barometers that were made with water. How tall are they going to be? If I use water to make my barometer, a column of water per square centimeter, which one weighs more? A column of water that's 10.3 meters. You're going to see that in the book all the time. That's about 33 feet. If you put a column of air, water, 10.3 meters tall, or a column of air, 30 kilometers tall, which one weighs more? Same diameter, same tube. They're equal. And what if I make a barometer out of mercury? Can you make it that small, can I? So that's something I want you to think about, all right? I want you to think about that, because Galileo could not figure out why his pumps couldn't pump more than about 33 feet. Or he didn't use feet, and he didn't use meters either. But he couldn't figure that out. But what is it about a pump? When you, some of you never had, have you ever done a pump, like a hand pump? You've been to some lodge or somewhere and they didn't have electricity, you had to, any of you ever done that in your life? You have? Have any of you pumped water out of a well, a hand pump? You have? Where were you? At camp? Okay, now, so what's happening, you got this tube, and you got these little rubber gaskets that are kind of flexible, and when you go like this, it actually takes the air out of the pipe and puts it somewhere else, right? And you go back for another, you take some more air, take some more out, and so you actually create a vacuum in that pipe. Well, so what? So what? The air is going to try to get in. It can't. It can't get in through the pipe. It can't get in through here. And I know you don't believe me. The air is going to push on the water underground. It's going to push the water underground and shove that water up that pipe. Now, which one, how high of a column of water can the air actually push up? What's the weight of any column of air per square centimeter compared to the weight of water? 30 kilometers of air equals about 10.3 meters of water. And so I know you're thinking, well, I'll just keep pumping harder and go ahead. Let's pump water that's 50 feet underground. It's not going to happen. It can't happen. The weight of the air is not great enough to shove that water up the pipe. Now, can I get an electric pump? Yes. Can I get an electric pump and start pumping water? I can do that. I can pump it all over the place with that. But if you're allowing the atmosphere to push the water up the pipe, that means no electricity, then you have a limit. There's a limit to what you can do. Does this make sense so far? Now, I have another thing I want to talk about here. So pressure, whoops, that's the wrong one. Okay, so we had atmospheric pressure about 100 kilopascals is normal atmospheric pressure. 1 atmosphere is normal atmospheric pressure. Here we have millimeters of mercury, 760 millimeters of mercury. That's true. 76 centimeters of mercury. And does anybody have a calculator with them? If you watch the news, they don't ever talk about millimeters of mercury. When they talk about what the air pressure is, what do they always say? Inches. Let's convert, okay? Convert 76 centimeters into inches. How about that? What's the conversion factor? 1 inch equals 2.54 centimeters. Somebody do me a quick conversion there. So divide this by 2.54. 30? So 29 point something? Okay. It's very, very close to 30 inches of mercury. Now, so if I were at sea level and I had a barometer and I was an American meteorologist, I might say we have 30 inches of mercury. That means normal atmospheric pressure. Yes? Okay, if I was a little more sophisticated and I was talking to people internationally, I would say 76 centimeters of mercury or 760 millimeters. That's the same thing. Now, what does it mean? What does it mean when the weather forecaster says 30 inches of mercury? It means today, the atmosphere can hold up a column of mercury, how tall? 30 inches. Now, let me show you what happens here. This is the neat stuff. This is pretty neat. I think I have a drawing here. Now, I'm going to give this lesson tomorrow, but I'm going to start the lesson today. We have waves of air. It's hard to see. You can't see them, but if you watch a meteorology, if you watch the weather forecast, they have a map, and you'll see a bunch of these. You'll see a bunch of these and a bunch of theirs. You ever seen those? H's and L's? All right, whatever that means. Just tell me what the weather's going to be, okay? I don't even know about those H's. And so what's happening is, today, there happens to be right here over Greensboro. Right now, the atmosphere, instead of being a piled up a bunch of air over Greensboro, we have kind of a depression of air over Greensboro. And that's called a low pressure area. Now, what would my barometer do? Let's go back to the picture of the barometer again. What would happen if the air coming over Greensboro weighed less? What if the weight of air above Greensboro weighed less than normal? Then it would push on this mercury less. And what would that allow to happen to? They say the barometer was falling. If they say the barometer is falling, then you have a low pressure area coming across Greensboro. And the barometer is one of the number one instruments used to forecast the weather. We even have weather balloons with barometers in them. And so I'll teach this lesson again tomorrow, but what happens is a low pressure area, high pressure areas are always trying to fill in lows. And so what happens is in the northern hemisphere, that's where we live, lows tend to be a valley of air. Then the barometer falls. And what happens is the air, though, is trying to fill it in, and because of the Earth's rotation, it fills it in, and it goes counterclockwise. It goes like this. And so you might hear, if you really want to pay attention to the meteorologist, you might see, if they said there was a low pressure here, they might say there was a counterclockwise flow of air. Now, if you're Greensboro, for example, let's say you're Greensboro right here, and let's say the low's coming right towards you, then what do you feel on the earth? Well, you'll feel air moving from here to here. And so they'll say, and winds are always named from the direction they come from. And these are coming from the what? Southwest. So the meteorologist might say, we will have southwest winds, and then, what happens when the low goes past Greensboro? I'm still going counterclockwise, right? What kind of winds? They'll say the wind's going to shift from southwest winds to what? Winds are always named for the direction they come from. What do you think? Just everybody got that? Now, I don't give the whole weather lesson today, but that actually what the barometer's helped me do. Now, what happens, and I believe this might happen this afternoon. This afternoon, I'd have to watch the weather. I didn't get to watch the weather. But they said it's going to be sunny. This afternoon is going to get sunny. Now, it's possible. It's possible it's because there's a high coming. Now, if a high is coming, a high pressure is like a mountain of air. And what will a high pressure do to a barometer? What if a bigger pile of air is sitting on top of the barometer? What's that going to do?
Push the mercury higher.
And we're going to say the mercury is rising. If the mercury is rising, that means it's a high pressure. Now, one thing about high pressure, because it is trying to flatten itself out, it actually will flatten itself out and move clockwise. And as it moves clockwise, it actually, instead of being a cloud maker, the other one was a cloud maker, this will be a cloud evaporator, like that. So a high pressure system would tend to evaporate the clouds, push them out of existence, like that. And I'll watch the weather. You can watch it tonight also. Maybe we can talk about it tomorrow. All right, so do you see the importance of a barometer? All right. Now, the other unit, like I said, even though I don't, when I was your age, I did. I had to learn the Torrs, I mean. But and I understand they wanted to give a little credit for the person who made the first mercury barometer. Yes.
I have a question about the thing you just talked about.
Okay.
Do the clouds cause the low pressure, or
Good question. Even though I can only give like a small weather unit, even the Earth being round has something to do with it. The fact that the sun hits some parts of the Earth at 90-degree angles, some not, and we have heat moving all over the place, and the heat moves the air around, and sometimes the air expands, sometimes it contracts, and sometimes it gets pushed. It gets pushed into piles, or pushed into stretched out into valleys. So the clouds are not causing it. It's like a signal. Hey, low pressure, I see. There must be a low pressure zone here. I'm seeing clouds forming here. If I watch clouds and all of a sudden the next hour they all disappear, it probably was a high pressure case. So the clouds didn't cause the low pressure. They were a sign that there is low pressure around you. Does that make sense to people? Okay. Anyway, to honor Torricelli, they used to call them Torrs. But a torr is the same as a millimeter of mercury. So if normal atmospheric pressure is 760 millimeters of mercury, then 760 torr is also normal atmospheric pressure. Yeah, I'm sorry there are so many ways of representing pressure. Oh, dang it, there's another one. There's another one. In the United States, we have, and you guys are actually more aware of this number than all the other numbers on this page. What's one more way you can represent pressure than you know, because you might have to go get air in your tires, you might have to fill up the basketball, and two people know. Anybody else? Raise your hand. Mason, you know?
PSI?
Yes. All right, so they do PSI. Okay, now, PSI is what? Pounds per square inch. Per square inch. All right. So PSI is pounds per square inch, and my tires in my car are about 32. If you open up your door, your driver's side door, if it's not in the door, it's in the other part of the door, but you'll see a little sticker there, and it'll say the manufacturer recommends this air pressure for your tires. If you've never seen that, do that today. Go look at it. And it'll tell you front tires, back tires. Sometimes they're the same. And they'll be in PSI. Now, does anybody happen to know? I don't have $1. Dang it. You do? Well, but I'd have to give it back to you. Wait. I have $1. Raise your hand if you know what is normal atmospheric pressure in PSI. Anybody? Okay, I'll say the $1. Okay, so has you ever heard of this? 14.7. That's about 15, okay? Now, I know it's hard for you to believe that right now, here's a square inch, ready? Inch, inch. There's a square inch. How many pounds of air are pushing on that square inch? About 15. How about the next square inch? About 15. 15. 15. There's no way I should be crushed, shouldn't I?
No.
But I'm not crushed by pressure. I'd be crushed by a difference in pressure, wouldn't it? So if it's pushing down with 15 pounds per square inch, if the fluids in my skin, if they can push back with 15, then I'm not going to really notice anything, all right? I don't really notice anything out here. One part of my body which notices pressure. What's the one part of your body that notices pressure differences before any other part? What do you think?
Your sinuses.
What is it?
Your sinuses.
Some people, it would be their sinuses. What else?
Your ears.
Yeah, eardrum. There's actually a pocket of air on the ear. There's a pocket of air on one side of the eardrum and another on the other atmosphere. And normally, if you don't have a cold or anything like that, normally they will equalize. If you were to go up in an elevator and you go, pretty fast, it might not equalize right away. So what happens? You feel something, right? And same thing in a plane. Plane goes up pretty fast. You might now be able to equalize fast enough, and you'll feel it in your ears, won't you? And so what do they tell you to do? How many of you, raise your hand if you've experienced this before? All right, what did you do about it? Okay, yawn, that'll do it. You can chew gum. You can move your jaw a little bit, like that. Make a push like that. And then you can actually equalize on both sides of the eardrum, and you'll feel a lot better. One of the hardest things is to have a little tiny baby, and you're going on an airplane trip. That's not good. Not good. Because the baby does not know why, but all of a sudden it's hurting. Its ears are hurting tremendously. If they don't have something like the suck on or something like that, they're just going to be crying and crying and crying. And if their ears never do equalize, they'll be crying the whole time. So they can't do anything. I bet you had to do it with scuba diving. Even though I have to be going up pretty far in the air to notice big differences, you probably right away, as soon as you go down, you notice a difference in air pressure there. Tell you a quick story. I'm getting certified in scuba diving, and I'm 17 years old, and we had in Indiana, and so we had to go. The only place we could get deep water, and there's a rock quarry. Okay. Anyway, so that nothing like going to the Bahamas or something like that. But we also, at the same time, we had a little kind of a celebration of everybody finishing the class and all that. And we had a contest. And one of the contests was they took a brick and a long rope, and they threw the brick in the water, and it had a little buoy on the top. And they gave everybody a paper clothespin. And they said, free dive, okay? Free diving means no tanks. And all you do is you go down, you put your clip with your name on it, all right? And they eventually pulled it up. Whoever went the deepest, they won a $50 gift certificate or something like that. I still remember, even when I was 17 years old, there was a guy there, and I was a kid, this is a man, and I remember he only had one arm. And you don't see that all the time. And it's okay, but he took this course. And there was something in him, such a strong drive. He wanted to win that contest. And he knew he couldn't go like this, like I could do it. He couldn't do like that. He only had one arm. He could kick in one arm, but he wanted to win that contest really, really badly. And when you go down there, first of all, you can go down as far as you want, and then your ears start hurting, things like that, and you try to clear it and stuff like that. And then you get a little nervous because you think, I better not stand here too long. I got to go all the way to the top in that same breath of air, And I clearly remember he came out that day. He did win, by the way. He wanted to win so badly. He had gone down so fast, so quickly, that he burst his eardrum. He did not allow time to equalize. He just knew one thing. He wanted to win that contest. And I always remember that. And I'm not trying to say that we don't all have that drive in us, but he had a higher drive than a lot of people. If I felt a little uncomfortable, and I said, that's enough. But he was going to win. He came up. He had to go to the hospital. He was bleeding. His ear was bleeding. Okay, I still remember that. Okay. All right. Now, what is interesting is what if I built a barometer with mercury, and what if the cross-sectional area here was larger? Now what? What if this was 1 square centimeter, and it's usually bigger than that anyway, but if this was 1 square centimeter and this was like 5 square centimeters, then how tall would the column of mercury be? I do want to do one more thing for you. This is a tricky question. You know why? Because it has to do with ratios. Remember I told you about that? I said the pressure was the same, wasn't it? Just because I have a bigger cross-sectional area, what about every square centimeter of that bigger guy? If this is 5 square centimeters, think about each square centimeter. How high of a column of mercury can each square centimeter be held up? 76 centimeters. How about the next one? 76 centimeters. So it doesn't even matter if the barometer is wider. It doesn't matter. It still can hold up a column 76 centimeters tall. Are you with me on that? It doesn't sound right, does it? But that's because it's a ratio thing. All right, I think what I'll do, I talked to a couple teachers. They donated, I got a whole bunch of newspapers. So I didn't have any newspapers at one time. I ran out. And I tried to use that paper back there, and that was bad. All right, so what we're going to do is, you stay right, you come back up just a little bit. We'll talk about this tomorrow. Well, first of all, I had some leftover things. Remember how we talked about how heavy air was? Remember that? So if I remember that, you? So you're going to pick that up. I said there is, if I have a lot of air sitting on top of it and I have almost no air underneath it, it is pretty thin. It's just like that. So I did want to show you one more thing. We didn't have left over. You know that density does explain lots of things. Have I shown this to you before? And so let me show you something else. Density does explain a lot of things, but a lot of things it doesn't. So some of it's just magic. And so what you can do is, for example, you take this ball here and you go like this. Wait a minute. Change. So some things are just magic. So I thought I didn't get to do it last time. We ran out of time, so I want to show you two. And I want to show you another one. If you think about this, I used to pass this around and I used to sanitize it. We're not doing that anymore. And what I would do is, if I watch, I'm gonna show you. Okay, now don't do that anymore. Okay, see? So all you do is tell it not to do it anymore, it won't. But what's actually happening is they have a tiny, tiny hole down here. See that? And if I cover the hole, then what happens? See this air here? If I try to put air in here, it's going to push back, isn't it? But what if I let the air out? So you can trick your brothers or sister, just make a little tiny hole right there. All right, well, here we go. Come on. Now, I know that I already proved to you that the weight of the newspaper is not enough to break a piece of wood, okay? So we got that. And so what I'm going to do is, I believe there's a huge amount of air sitting on top of that. All I really didn't do is try to get the air to not be underneath the newspapers. That's why I'm doing that. There's no glue like that. I'm just trying to get a lot of air out from underneath the newspaper. Come on, baby. Oh, what happened? Can I tell you that 3 weeks ago, I did this in elementary, and it worked every time. Every time. Okay. If this doesn't work this time, I'm not by the holes, that's good. See, you're not convinced, are you? Works for me, okay? I think it works for me. Oh, okay. All right. I do need the paper. I need the paper, not the hair. Now, let me try it another way. I'm really disappointed with this. How can I get that paper not to? They keep making newspapers cheaper and cheaper, and I worked at it not too long ago. All right, let me think. This should do it. paper tears, the air gets underneath it a lot. So if I can get it to the paper not to tear, don't tear. Oh, okay. Unfortunately, after you do it 5 times, I didn't hear any applause, that's okay. But actually, okay. As long as the paper doesn't tear, as long as the paper doesn't tear, then you can see that the weight of that air was enough to kind of hold that wood down there, and I could break it. And I don't know why. I don't know why it was tearing and tearing and tearing. I don't know. All right, it worked. The last thing I'm going to show you, I think I'm done actually. Tonight, I would like you to, you should be reading the chapter, and you should actually doing your homework a little bit on the chapter. I want you to think about the idea of a take-home test on Thursday night. I don't think you're going to have any of the homework. I don't think you want to come back after vacation, and I don't think you want to do that. So I'm going to try to hurry a little bit, but I think I could possibly be done by Wednesday. Maybe.